We're going to draw our program of videos on complex numbers to a close by having a look at the roots of unity and some geometrical applications of the roots of unity. To begin with, we need to pull together some key facts and introduce one or two new key facts. First of all, in Further Maths Unit 1, we saw that if we multiply a complex number by cos alpha plus I sine alpha, or equivalently multiply the complex number by e to the I alpha, then that has the geometrical effect of rotating the point representing the original complex number by an angle alpha anticlockwise about the origin. We also introduced the idea of the modulus of the complex number z, which is just the square root of the real part squared plus the imaginary part squared. So the modulus of x plus iy is the square root of x squared plus y squared. Now that means that the modulus of z squared is x squared plus y squared, which is the same thing as x plus iy times by x minus iy. So the modulus of z squared is the same thing as z times by the complex conjugate of z. And the complex conjugate of z can either be written as z bar or z star. And we also saw in Unit 1 that the modulus of z minus w gives the distance on the Argand diagram between the point representing the complex number w and the point representing the complex number z. During earlier videos for this particular module, we have seen that the nth root of the complex number r e to the I theta can be written as r to the 1 over n, in other words the nth root of r, times by e to the I theta plus 2k pi divided by n, where k can take the values 0, 1, 2 all the way up to n minus 1. And we can rewrite that in the modulus argument format to say that the nth roots of the complex number, which has modulus r and argument theta, are of the form r to the 1 over n, in other words the nth root of r, as the modulus of all of the roots, and the argument of the roots take the form theta plus 2k pi divided by n, where k can take any of the values from 0 through 1, 2, all the way up to n minus 1. And when we plotted on an Argand diagram the nth roots of the complex number re to the I theta, they are equally spaced around a circle of radius r to the 1 over n, and the centre of the circle is the origin, which means that the points representing the roots are going to form the vertices of a regular n-sided polygon. Now we're going to extend or apply the results of key facts 2 to looking at the nth roots of unity. Now unity just means the number 1, so we're going to look at the nth roots of the complex number 1 plus 0i. And using the results of key facts 2, we can say that the nth roots of the complex number 1 can be written as e to the I times 2k pi over n, for k equals 0, 1, 2, all the way up to n minus 1. So in other words, we've got 1 e to the I times 2 pi over n, e to the 4 pi, e to the I times 4 pi over n, e to the I times 6 pi over n, all the way along to e to the I times 2n minus 1 pi divided by n. And if we could write omega as being e to the I 2 pi by n, then the list of the roots can be written as 1 omega, omega squared, omega cubed, all the way up to omega to the n minus 1. If we plot on an Argand diagram the nth roots of unity, they're going to be equally spaced around a circle of radius 1, whose centre is the origin. For all values of n, 1, or 1 plus naught I, will be a root of unity, so this is going to be one of the vertices of the polygon. If n is even, then minus 1, or minus 1 plus naught I, will also be a vertex of the polygon. And because the equation z to the n equals 1, which is what we're solving when we're finding the roots of unity, is a real polynomial, then the complex roots will appear as complex conjugate pairs, so the real axis is going to be a line of symmetry of the polygon. So if we consider the seventh roots of the unity, then the seventh roots of unity can be written in the form e to the I 2k pi over 7 for k equals 0, 1, 2 all the way up to 7 take away 1, which is of course 6. E to the I times nothing is e to the nothing, which is 1. E to the I 2 pi by 7, e to the I 4 pi by 7, all the way up to e to the I 12 pi by 7. And if we write omega as being the first non-real solution, that is, omega is e to the I 2 pi by 7, then the list of roots is 1 omega, omega squared, omega cubed, all the way up to omega to the 6. Plotting them on an Argand diagram, we can see that the points representing 1, omega, omega squared, omega cubed, etc. form a regular heptagon, regular seven-sided polygon, and the centre of that polygon is indeed the origin. And in this second diagram, we've got the seventh roots of unity again shown, but this time we're also showing the results of working out z0 plus z1, z0 plus z1 plus z2, then z0 plus z1 plus z2 plus z3, then z0 plus z1 plus z2 plus z3 plus z4, z0 plus z1 plus z2 plus z3 plus z4 plus z5, and finally z0 plus z2 plus z3 plus z4 plus z5 plus z6. And if you look at the effect of adding all of them together, you notice that we get back to the origin. So this is suggesting that z0 plus z1 plus z2 plus z3 plus z4 plus z5 plus z6 is equal to 0. We're now going to try and generalize this result. And the result we're going to try and prove is that the sum of all of the nth roots of unity will be 0. So as before, let's write omega as e to the I 2 pi by n, in which case we can write the nth roots of unity as 1 omega, omega squared, omega cubed, up to omega to the n minus 1. Now, one way of looking at the sum of the roots is to say that's precisely 1 plus omega squared plus omega cubed all the way up to omega to the n minus 1. And that, of course, is the first n terms of a geometric progression with first term 1 and common ratio omega. We know that the sum of a GP can be written as a, where a is the first term, times by r to the n minus 1 divided by r minus 1. So with a equals 1 and r equals omega, we know that the sum of that GP is going to be omega to the n take away 1 divided by omega take away 1. But Omega is an nth root of 1, so we certainly know that omega to the n is equal to 1. So our sum of the roots, 1 plus omega squared plus omega cubed, all the way up to omega to the n minus 1, is actually equal to 1 take away 1 divided by omega take away 1. We know omega isn't equal to 1, so we can be certain that what we've got is 0 divided by something other than 0, which certainly gives me 0. An alternative way of proving the same result is to say that 1 omega squared all the way up to omega to the n minus 1 are the roots of the equation z to the n minus 1 equals 0, and that the sum of the roots is always equal to minus b over a, where b is the coefficient of z to the n minus 1 and a is the coefficient of z to the n. In this case, the coefficient of z to the n minus 1 is 0. The coefficient of z to the n is 1. So what we've got is the sum of the roots must be negative 0 over 1, which is 0. So, to summarise, if we've got omega is e to the I 2 pi by n, then we know that omega to the n is equal to 1. We know that the roots of the equation z to the n equals 1 are 1 omega squared all the way up to omega to the n minus 1. And that tells me, or the factor theorem tells me, that a factorisation of z to the n minus 1 would be z minus 1 times z minus omega squared all the way along until a final factor of z minus omega to the n minus 1. And we have also shown that 1 plus omega squared all the way up to omega to the n minus 1 is equal to 0. So let's start using some of these results to answer some questions. So in example 1, we've got if omega is e to the I 2 pi by 3 and alpha is 3 plus 8 omega, beta is 3 plus 8 omega squared, we've got to prove that alpha plus beta is equal to minus 2, and we've got to determine the value of alpha times beta. Well, the cube roots of unity are 1, omega, and omega squared. So we certainly know that omega cubed is equal to 1. And we also know that 1 plus omega squared is equal to 0. Now, that means that alpha plus beta is 3 plus 8 omega plus 3 omega squared plus 8 omega squared, which we can rewrite as 6 plus 8 times omega plus omega squared. But I know that 1 plus omega plus omega squared is equal to 0. So that certainly tells me that omega plus omega squared is minus 1. So I can now say that alpha plus beta is 6 plus 8 times minus 1, which is indeed minus 2. Alpha times beta is 3 plus 8 omega times 3 plus 8 omega squared. So that gives me 9 plus 24 omega plus 24 omega squared plus 64 omega cubed. Now I know that omega cubed is equal to 1. So I've got 9 plus 24 lots of omega plus omega squared plus 64. As before, I know that omega plus omega squared is minus 1. So I've got 9, take away 24, add 64, which gives me 49. So alpha times beta is 49. Now I've got to now find a quadratic equation with integer coefficients whose roots are going to be alpha and beta. Well, a quadratic equation with roots alpha and beta would be x minus alpha times x minus beta equals 0. In other words, x squared minus alpha plus beta times x plus alpha beta equals 0. I know that alpha plus beta is minus 2. I know that alpha times beta is 49. So the equation I'm looking for is x squared plus 2x plus 49 equals 0. Moving on to a second example, the complex number z1 e to the I pi by 7 is represented on the Argand diagram by the point A. We've got to find complex numbers z2 and z3 represented by the points B and C respectively on the Argand diagram, such that the triangle ABC is an equilateral triangle with the centre the origin. And then finally we've got to find what's the smallest possible value of n for which z1, z2 and z3 are all nth roots of unity. So let's start with a diagram. We know that z1 has got a modulus of 1 and an argument of pi by 7. The 3 points on the equilateral triangle lie on a circle of radius 1 and centre the origin. Now the angle between A and B and then B and C must be a third of 360 degrees, in other words 120 degrees or 2/3 pi. To obtain B, I simply need to rotate the point A about the origin by 2 pi by 3. So this means that the modulus of z2 is still going to be 1, but the argument of z2 is going to be pi by 7 plus 2 pi by 3, which is 17 pi by 21. So we can say that z2 is going to equal 1 times e to the I 17 pi by 21. In other words, z2 is e to the I 17 pi by 21. Similarly, we can obtain the point C from the point B by rotating the point B anti-clockwise around the origin by 2 pi by 3 again. So this means that the modulus of z3 is still going to be 1, and the argument of z3 is going to be the argument of B, which was 17 pi by 21, add 2 pi by 3, and that gives me 31 pi by 21. So I can now say that the complex number z3 has got a modulus of 1, an argument of 31 pi over 21, so it can be written as 1 times by e to the I 31 pi by 21, in other words just e to the I 31 pi by 21. Now what we also asked is what is the smallest positive value of n for which z1, z2 and z3 are all nth roots of unity. Well, z1 to the power n is going to be e to the I pi by 7 to the power n, and we want that, well, which is the same thing as e to the I times n pi by 7. Now if that is going to be equal to 1, then I must have n pi by 7 being a multiple of 2 pi, because 1 is the same thing as e to the 0i, or e to the 2 pi I, or e to the 4 pi I, or e to the 6 pi I, etc. So I must have n pi divided by 7 equaling 2k pi, where k is a positive integer, which means that I must have n equals 14k, where k is a positive integer. So the first positive integer that satisfies that for me would be 14, but we've also got the possibility of 28 or 42 or 56, etc. So n must be a multiple of 14. But we need z2 to the power n to equal 1 as well. Now z2 to the power n is e to the I 17 pi over 21 to the power n, which becomes e to the I 17n pi divided by 21 equals 1. And as we said before, if we're going to have 1, we must have then 17n pi divided by 21 must be 2k pi, where k is a positive integer. Now, multiplying up by the 21, we've now got 17n must equal 42k. Now, since 17 and 42 have no prime factors in common, this means that n must be a multiple of 42. Similarly, if we consider z3 to the power n, we're going to end up with the statement that 31n must equal 42k, which implies that because 31 and 42 have no prime factors in common, that n must be a multiple of 42. So we now know that for all three conditions we need n to be a multiple of 14, n to be a multiple of 42, and n to be a multiple of 42. So in other words, the smallest possible value of n that we can have will be 42. So if I have n equals 42, I've got z1 to the 42 is the same as z2 to the 42, is the same as z3 to the 42, which is equal to 1. Moving on to the next example, we've got a regular hexagon in the argand diagram, has its centre at the point representing 5 plus 3i, and a vertex at the point representing z1, which is equal to 8 plus 7i. We've got to determine, in any form, the complex numbers representing the other vertices of the hexagon. So, we'll start with the sketch and put on the information that we've got. So we know the centre of the hexagon is the point 5 plus 3i, and we know that 8 plus 7i is one of the vertices. So first of all, we're going to move the centre of the circle to the origin, which will make the subsequent working a lot easier. So that will take z0 to 0 plus 0i, which we'll call w0, and it will take z1 to 3 plus 4i. And there we've got our new hexagon at that stage. Now, having done that, if we look at the complex number w1, the complex number w1 has got modulus square root of 3 squared plus 4 squared, which is 5, and the argument of w1 is going to be tan to the minus 1 of 4 over 3, and for the moment we'll just call that angle alpha. Now the great beauty now is that having worked out what w1 is, it's now very easy to work out what w2, w3, w4, w5 and w6 are. So w1 we've got in its modulus argument form, it's got modulus of 5 and an argument of alpha, so we can say that w1 is 5e to the I alpha. So w2, well, we've got a regular hexagon, so the angle between the angle at the centre made by consecutive vertices is going to be pi by 3. In other words, for w2, we can say that w2 is the image of w1 after an anticlockwise rotation of pi by 3 about 0. So w2 is simply going to be w1 times by e to the I pi by 3. So that is 5e to the I alpha times by e to the I pi by 3. In other words, we've got 5e to the alpha plus pi by 3. Similarly, w3 is the image of w1 after an anticlockwise rotation of 2 pi by 3 about the origin. So we can say that w3 is w1 times e to the I 2 pi by 3. So that's going to be 5e to the I alpha times by e to the I 2 pi by 3. So that gives me 5e to the I times alpha plus 2 pi by 3. And we can work exactly similarly to get W4, W5 and W6. So we've got WK, if you like, is given by 5e to the alpha e to the I times alpha plus k minus 1 times pi by 3 for k equals 1, 2, 3, 4, 5 and 6. But we don't want the W values, we want the Z values. So to get back to the Z values from the W values, we just need to remember the relationship between them. We had WK was equal to ZK minus 5 plus 3i, so ZK must simply be WK plus 5 plus 3i. So we've now got ZK is 5 plus 3i plus 5 times by e to the I alpha plus k minus 1 pi by 3 for k equals 1, 2, 3, 4, 5 and 6. Okay, and the only thing we have to remember is that alpha is tan to the minus 1 of 4 upon 3. Moving on then to our final example, we have A, B, C, D, E and E are points on a circle of radius 1 which forms a regular pentagon. We must prove that AB squared plus AC squared plus AD squared plus AE squared is equal to 10. So let's define the axes so that the centre of the pentagon is the origin and the vertex A is the point 1, 0. So there we are, there's our sketch for our pentagon. Now the cunning thing on this question is that we're going to introduce omega, which is e to the 2 pi I by 5. Now if we introduce omega, we know that omega squared, omega cubed, omega to the 4, together with 1, are the 5 fifth roots of unity. And we know that these 5 points form a regular pentagon. Moreover, this regular pentagon has as its centre the origin, and the circle containing the 5 units, the 5 roots of unity, has radius 1. In other words, it's exactly the pentagon that we're considering in the question. So, if omega is e to the 2 pi I by 5, then on the Argand diagram, omega represents the complex, omega is represented by B on the diagram. Omega squared is represented by C, omega cubed is represented by D, and omega to the 4 is represented by the point E, and the point A represents the complex number 1. So the pentagon that we've drawn there on the Argand diagram represents the points 1, omega, omega squared, omega cubed, and omega to the power 4. We also need to just remember that omega and omega to the 4 form a complex conjugate pair, and omega squared and omega cubed are also a complex conjugate pair. So having made those observations, what we're interested in then is AB squared plus AC squared plus AD squared plus AE squared. Now AB squared is going to be exactly the same as AE squared, and AC squared is going to be exactly the same as AD squared. So the first thing we can say is that symmetry tells me that AB squared plus AC squared plus AD squared plus AE squared is twice AB squared plus AC squared. Now, AB squared is the distance between Z1 and Z2 squared, which is the modulus of Z2 minus Z1 squared. And similarly, AC squared is the modulus of Z3 minus Z1 squared. So that, in terms of omegas, is twice the modulus of omega minus 1 squared plus the modulus of omega squared minus 1 squared. Now remember, we made the comment that the modulus of Z squared is the same thing as Z times by the complex conjugate of Z. So I can say that the modulus of omega minus 1 squared is the same thing as omega minus 1 times by the conjugate of omega minus 1. Similarly, the modulus of omega squared minus 1 all squared is the same thing as omega squared minus 1 times by the conjugate of omega squared minus 1. Now the conjugate of omega minus 1 is simply the conjugate of omega, take away 1. And similarly, the conjugate of omega squared minus 1 is simply the conjugate of omega squared, take away 1. Now, we've already commented on the fact that the conjugate of omega is omega to the power 4, and the conjugate of omega squared is omega cubed. So substituting these in for the conjugate of omega and the conjugate of omega squared, we have that. So the expression for AB squared plus AC squared plus AD squared plus AE squared is now 2 lots of omega minus 1 times omega to the 4 minus 1 plus omega squared minus 1 times by omega cubed minus 1. So multiplying out now, we've got 2 lots of omega to the 5 minus omega to the 4 plus 1 plus omega to the 5 minus omega squared minus omega cubed plus 1. So that's 2 lots of 2 omega to the 5 plus 2 take away omega plus omega squared plus omega cubed plus omega to the 4. Now we know that omega to the 5 is equal to 1. And we also know that 1 plus omega squared plus omega cubed plus omega to the 4 is 0. So therefore omega plus omega squared plus omega cubed plus omega to the 4 is actually equal to minus 1. So what we've now got is 2 times by 2 plus 2 minus minus 1. In other words, we've got 2 times 5, which is equal to 10. So we've proved that AB squared plus AC squared plus AD squared plus AE squared is equal to 10. So we've used complex roots of unity here to prove a rather nice result about the geometry of regular pentagons. And that concludes our work on roots of unity and some geometrical applications.